Good evening, I'm Tabitha Binding. I work for Timber Development UK, and I'd like to welcome you to tonight's webinar. Timber Development UK is organising this challenge along with our partners Edinburgh Napier University, NMITE, which is a new model institute for technology and engineering, and the Passivhaus Trust. And this challenge is for students and 2021 graduates studying built environment subjects at universities across the UK. And so the Southside Challenge is a interdisciplinary cross-university team challenge for participants between teams of 4 to 8. And we want those teams to design, engineer, specify and cost one community building from timber to Passivhaus standards. You've got a budget of 1.6 million, and the 3 clients expect to have a space of about 800 square meters. Now, it could be on 1 level or it could be on 1.5 levels. The site for the physical building is on the boundary of 2 fields, and you'll find there's a Google Maps with a pin in it, and it's a greenfield site. I mean, ignore the layout here. It is, and that building, that's just an artistic image. We hold the information on the TRADA website. We record these and put them up on YouTube, and obviously you can register for the next talks on our Eventbrite page. So tonight we've got timber buildings performing as intended, and we have 3 speakers. We've got Diana Waldron of WoodKnowledge Wales with Building Performance Evaluation, Professor Sean Smith of the University of Edinburgh on timber building acoustics, and Gwilym Still of Max Fordham on heating, ventilation and hot water. And with that, I would like to hand over to you, Diana.
Thanks, Tabitha. Let me share my screen now. Okay, can you see this in full screen now?
Perfect.
Fantastic. Well, thanks for inviting us to that tonight, Tabitha. It's great to be here. My name, as Tabitha mentioned, my name is Diana Waldron, and I work with WoodKnowledge Wales. And my main focus tonight, I'm going to talk to you about building performance evaluation. So before I move on, I want to thank contributors to this presentation, my colleagues Gary Newman, David Hedges, as well as collaborators Julie Godfrey and Susie Diamond. So just to give you a brief background about myself and about WoodKnowledge Wales. So my academic background is on, I did my undergraduate on architectural engineering at Cardiff University, and then I moved on to do my master's on environmental design of buildings. And then I also did my PhD in the topic of plants and architecture, mainly focused on case studies related to vertical farming and building simulation. This PhD also at the Welsh School of Architecture. So before I joined WoodKnowledge Wales, I worked on a number of research projects, including the Low Carbon Research Institute, the Sustainable Building Envelope Demonstration Project, and other projects as well. And before I was working full-time with WoodKnowledge Wales, I was initially based at Cardiff Metropolitan University, working with the Homegrown Home Project and WoodKnowledge Wales. And I'm going to talk to you, the work that I'm presenting today is one of the outcomes of the Homegrown Homes project. So I'm going to talk to you a little bit more about that project in the next few slides. And so when I was based at Cardiff Met Uni, I was leading the Building Performance Evaluation work package. And then following the culmination of the Homegrown Homes project, I joined the WoodKnowledge Wales team to continue with the engagement with housing providers, aiming to increase the implementation of building performance evaluation techniques in the social housing sector. So basically taking that, the outcomes and that research that we did during the Homegrown Homes project and making sure that it's being implemented in the delivery of homes. And the main aim of my role at WoodKnowledge Wales is to assist housing providers to minimize the performance gap by measuring the real performance of buildings and develop strategies to tackle potential issues to provide better and healthier homes for occupants. And I'm part of so this is the whole team. Actually, I'm missing one person that joined us recently, our colleague John. And even though it's a small team, we like to work in collaboration with other people. We have a great list of members in our board. You can see lovely names here, including Tabitha. So we even though we're only 8 of us, we have a large network of collaborators. In this slide, I mentioned the collaborators that we work with focus on building performance evaluation, post-occupancy evaluation, and embodied carbon. But obviously our external collaborators is not limited to this slide. We have a lot of colleagues in the area of forestry, timber manufacturing, etc. So feel free to contact us if there's any topics related to anything of what I'm talking today. If you'd like to contact me to know a bit more, feel free to do so. Our collaborators are in the area of academia and in the area of the industry and housing providers as well. And our community continues to grow. WoodKnowledge Wales is a not-for-profit organization. So this is a list of our members, and it's thanks to our members that we can do the work that we do. And at WoodKnowledge Wales, we like to think of ourselves as resolutely practical. We like to get things done. We don't like to talk too much about things. We like to, just get our boots on and go and be in the forest, see how is the timber production, be it the timber manufacturers, see how the line is working, and be at the construction sites to see how the buildings are put up. And then also we also ourselves go and talk to occupants to undertake a post-occupancy evaluation. We're purposefully driven. So we work with housing associations, with local authorities. We like to be on the ground, seeing that the research that we're doing is actually being implemented. We like to be open and collaborative, and we're humble in approach in the sense that we, as much as we know the value of the knowledge we have in-house, we also recognize that there's a lot of value in all other organizations, and we like to work together to go further, to achieve more. Like, we do believe that we're stronger together. So as I mentioned earlier, last year we culminated the Homegrown Homes project, but it was only the research phase. We have been since we finished this project early last year, we have been working on the next stage of the Homegrown Homes project, on the implementation stage. So the research phase was mainly focused on 3 main topics. So the research on the delivery of more and better homes in Wales. Even though our context was Welsh, all our learning is easily transferable to the rest of the UK. And we are also working with international partners in terms of European partners and international partners to bring this knowledge at an international level as well. But we can't talk about delivering better homes without also talking about the supply chain and the manufacturing chain. So a significant part of the research we did was on timber manufacturing and on the production of timber. So how to move forward the implementation and the growth of locally homegrown timber, basically. So working with forestry and landowners. So the way we achieved this during the Homegrown Homes project was by doing a lot of applied research. So working with example projects, case studies, where we did a lot of the applied research. So we were doing obviously a lot of the reading, literature review at the same time as we were talking to the housing providers, and they were coming to us with the various problems that they're facing, and we were finding the solutions to these problems. And we then gather all the knowledge and made it public and share it. So in our website, you'll find a lot of free resources. All of the outcomes from this project are all available there. We have a Google map when you can see the location of the different case studies that we have. And this Google map has various layers as well. So it's not just about the housing projects, but as well about the various other projects that we did in terms of forestry, timber manufacturing, and again, not only focus on building performance evaluation, but also embodied carbon. So you'll find some case studies in our Google Maps. And I just wanted to include this slide here of some of the main outcomes that I feel are most relevant for the topic that we're talking tonight. And again, you find these things in our website. So we developed this infographic at the end of the Homegrown Homes project, where we, based on all the literature review and the work that we've done, we set out these 5 key stages to achieve net zero whole life carbon, and establish some targets based on the literature, based on what is already being done out there, and put it all in one place. Here are a list of some of the publications that you can find on our website. So embodied carbon, zero carbon homes, these are all documents that actually are have been published and freely available in our website. But today we're going to focus on, let me go to the next one, on the building performance evaluation guidance. And even though it's only 4 in here, if you go to our website, you're going to find that it's an endless list of not just publications, but podcasts, webinars. There's a lot of resources for you to find if you're interested in knowing a bit more in detail. So moving to the topic, to the center of the central topic, what is building performance evaluation, also known as BPE? So I know this slide is really wordy, but I also know that you're going to use the slides as some of your notes. So I wanted to include here some of the main concepts that I want you to keep in mind. So BPE covers a range of tools and techniques that can help determine how well a building and its elements are performing. Effective BPE starts at the briefing and the design stage and continues during the lifetime of the building project, including post-occupancy. So in general, a comprehensive BPE should take place at the design stage, construction, completion and handover, occupancy, and post-occupancy evaluation. But we know this is not always the ideal world. So sometimes you have to make do with what you have. So sometimes you can't implement building performance evaluation at the design stage. So there are ways that you can implement BPE at halfway through. But the ideal scenario is if you can think about these at the early stage, that's when you're going to get the best results. And why is this important? Why is building performance evaluation important? So besides the obvious reasons that when you provide more efficient homes, that means you will potentially lower the energy bills and promote improve health and well-being for occupants and provide a better environment. There's also mandatory standards that are catching up, even though the minimum standards haven't always been on the side of the improved performance of buildings and embodied carbon. The standards are catching up. And for example, in the Welsh context, the government published the latest WDQR, which is the Welsh Development Quality Requirements, with the document Beautiful Homes and Spaces, when they actually make it mandatory a lot of these building performance evaluation standards, a mandatory standard, not a nice to have scenario. But beyond that, professional organizations are also demanding better standards for all. So for example, the Building Performance Network, they established a joint position statement on operational performance. And here I included a link where you can go and find more information, where you can see which organizations are actually part of this joint position statement. And besides building performance evaluation, there are further sustainability issues such as embodied carbon that are also being taken more seriously. So for example, only a couple of weeks ago was the first bill passed at the UK Parliament, where they will make mandatory to calculate reduce the embodied carbon footprint of new buildings for the first time. So these only happened 20 days ago. And even though it's only at the initial stages, they are now moving in that direction where housing developers are going to be held accountable for the impact of the embodied carbon of the buildings that we are delivering. But in reality, what we really advocate is just get the basics right. It's just appalling that more often than not, buildings don't perform as they should. So I wanted to bring to your attention this particular document. They published by the Design Council, where they established that they work with people to create better places, better products, and better processes, and all of which leads for better performance. So it's like you can get, by providing better performing buildings, you're just gonna provide better quality and better living standards for people. So it's about providing buildings that are fit for purpose. So a home that is affordable, a home that gets the basics right, and a home that does what it's meant to be doing. And it's shocking that only 56% report that their homes get the basics right. And this is the bare minimum, let alone if we think about going beyond the minimum. So in practical terms, how can building performance be approached? Let me just get this. So to begin with, if we think about it almost like having taking baby steps, and you need to think about the key elements of building performance techniques. So when you're talking about the performance of a building, you obviously need to think about people, about the indoor environment, about energy and water. And our colleagues that are going to be talking after me are going to mention some of these important parameters as well. But once you start taking these baby steps, then the earlier you can think about this, the earlier you can start planning the integration of these items. And you can start setting targets and reviews. And I'm going to show you what sort of tools we develop to help you to set these targets and to take these baby steps in a way, so that you can plan to take the measurements that need to be taken and to check whenever it needs to be checked. And also this includes post-occupancy evaluation. So when you get the basics initially, then you kind of break this down into what do you mean by these basic steps. And so you kind of come up with a list of important key issues that you need to consider to talk about building performance evaluation and to actually put in place what you need to do to achieve these measurements that you need to get to make sure that you're delivering the buildings that you need to be delivering. So we developed, as I mentioned, the building performance evaluation guidance from the Homegrown Homes project, and we split it into 2 packs. So the tool pack, which has like sorry, I keep getting pop-up messages of people coming in, so forgive me if I look a bit distracted. But yeah, so it's all good. So the tool pack focuses on these different documents, which is almost like a condensed part of the information, and the guidance has like more details. So if you look at the tool pack and there's a particular topic that you want to know a bit more about, then you go into the guidance and read about the background, about the references, about the different targets. But for practical terms, I recommend you to look at the tool pack and go from there. So building performance is like a gradual approach. So if you start from what's regulatory, what's the minimum requirement, and then look into the core BPE strategies that we mentioned that are included in that guidance that I'm talking about. And then once you look into the core strategies, you're already doing most of the legwork that you need to do in terms of building performance evaluation. And then when you take care of the core requirements, then potential problems may arise that will lead you to want to do more detailed BPE. So for example, thermography, something that you may not need for every project, but if there's something that you want to know more details, if there's a particular thermal bridge detail that you want to know in reality how it's performing, then you might want to implement thermography. And that's just an example of many of the different techniques that are available. So how to embed these BPE techniques? So in the tool pack, which is available for you to download, the first page is this, what we call the BPE timeline. So at the different stages, there are different methods of BPE that you can implement. So at the early design stage, at the design and development, at the construction, the completion and handover of a project, and in use. And to help you to implement BPE at the different stages, we developed a client sheet and one-pagers and a prompt sheet to take you through each of the stages. So each of these pages you'll find in that tool pack that I mentioned. And at the end of the slide, I provide a link for you to just click and download all of these resources. And so besides what I just showed you in this slide, So as I mentioned, BP are various different techniques. So they're very detailed in the guidance, but we also wanted to provide you with one pager that you could potentially use with key players of your design team. So they provide like an overview of each of the building performance evaluation techniques for you to share with potential clients or newcomers of your team. So you can say, if you get someone that is going to be focusing mainly on the air tightness or on the energy consumption calculations. So you've got a one pager with key elements and key information on why is this important, when is it done, how, what is the potential cost, and what to do next. And it provides a lot of prompts and tips if you want to focus on any of these particular techniques, basically. And also at the prompt sheets for the visits and the design reviews. So when you want to do the follow-up, when you want to do post-occupancy evaluation, what are key issues that quite often go wrong? And so these one pages are quite useful, I found, because at the moment there's a lot of building performance evaluation literature, but not enough condensed what do you need to do on the ground to implement it. So that's what we were trying to tackle with this. We also feel that these tools may, it's no one solution fits all. So any feedback that you can give us on how these tools have been useful to you, or if you think, oh, this can be improved if you included an extra sheet in a certain way, that would be really valuable for us to improve it for the future. So to begin with, the client sheet at the design stage, this is a resource that we felt important, where you can actually set specific targets, focusing on specific factors like overheating, for example, or energy performance. And how we didn't want to provide one specific target, because targets are very much dependent on the typology of building that you're designing, on the materials that you're using, on the budget as well. But what we do include in the guidance are references of what targets are used, and I'm going to show you some in here. And then at the end here, the right hand side, these are references to the one pagers and the prompt sheets that I mentioned earlier. So for you to consider when you're doing setting out the targets. And let me just I will zoom in on this in a minute, but here is I'm giving you an example of how you can set some targets based on references. For example, if you want to set up Passivhaus targets or RIBA 2030 targets, or the targets that we include in the home references. So here I then outline some of the targets that you could include as part of that guidance. And let me zoom in here so you can see a bit better. So in terms of overheating, for example, the RIBA 2030 stages, they have a particular target that they like to include when they do, for example, simulation. Passivhaus does as well. But one thing we found really useful is the Good Homes Alliance tool, that not all projects can afford doing a 3D simulation. So the Good Homes Alliance overheating tool, again, information on this is included in the guidance, and it's a free tool for you that you can download one page to include at the design stage of your building. So I highly recommend for you to go and look at this tool, because it's kind of considering overheating risks, but at really early stage, which means you don't have to spend a lot of money in simulation programs and things like that. And anyway, I will leave you with this slide for you to look at the different targets that you could potentially use for your client sheet. And then in the program, so also in the tools, we included this table that is almost like a checklist of the different things that you can include at the different stages of your design project. And this is an example of a client that came to us. We couldn't be part of the design process, but they already had occupants in this house that they implemented. They did a retrofitting measurement, and they wanted to implement post-occupancy evaluation. So this is an example just to show you how we put a proposal together of how we work with experts on taking measurements of U value of the building envelope. And so these specific measurements can be compared to what was designed. And that's how we then identify if there's a potential performance gap of what at the design stage, what targets they had, and what actual U value measurements or air tightness measurements you're getting for this building. We also put proposals for post-occupancy evaluation so that you can get occupants' satisfaction. And we also promote the idea of including the embodied carbon assessment. In my last slide, where I provided references, I also include a link to one of our webinars focused on embodied carbon assessment, where we had a really interesting talk from various experts in this area. And as I say, there's also a guidance from WoodKnowledge Wales in this area for you to look at if you're interested in knowing more about embodied carbon assessment. And thermography is again another type of building performance evaluation that you can include. I only mention it here because some thermography is only done indoors, and depending on the type of project, you might want to do it outdoors as well. So some of the key recommendations when you go through this process is record every step. So these tools are meant to help you to try to understand all this process and develop a process, but only you will know what works for you and what's the best way for you to record this process. And the idea is for you to come back to it at a later stage to check if you're doing what you set out to do. And also not just at the post-occupancy evaluation stage, but maybe a few years later when you want to compare a few cases and what you learned from previous projects, you can come back to it. Building performance evaluation is a team effort, so embedding performance in the project team culture is highly recommended. We strongly advise for project managers, for example, to appoint each task of this list to different members of the team, because it can be overwhelming if you don't spread the load of work. So communication is really key. So discussing targets with the design team and contractors. There's evidence that a lot of the performance gap happens due to this miscommunication between the design team, the contractors that are actually building the buildings and trying to get the design right, and then the handover team. So this trying to maintain this communication is really important, and that's why we feel these tools will be really valuable to try to help pass this communication, this information along throughout the lifetime of the development of a project. And improve with every project. Prepare for the next stage and establish your BPE learning loops as well. So here is a list of the various references that I've mentioned here, but also webinar links. If you have the time, last autumn we had a Wood Build event, and here I share with you two of the videos that I think are most relevant with this related to this talk. But we had various other webinars. If you had the time to look at them, feel free to access them, or contact me if you want to know more. Other sessions were about the procurement of timber buildings and other really interesting sessions. And yeah, thanks for listening, and I will be happy to take questions at the Q&A.
Thank you so much, Diana. That was incredibly comprehensive and such a useful resource.
Oh, thank you.
Thank you for coming, because I can hear your lovely children in the background. So sharing your children's time with us is really appreciated.
No, thank you for having me. I'll
stop
sharing now.
Yeah. And we hand over to Professor Sean Smith, who I said is going to talk to us all about acoustics.
Thanks very much, Tab. I'll just share my screen. Can you see that just now?
Yeah, we can see it. Yeah, that's it. Perfect.
Yeah,
it's in full screen.
That's great. Well, good evening, everyone, and thanks very much to Tab Binding and also Professor Robert Hairstans and NMITE for the invitation to present. Sometimes we think that acoustics maybe not quite as sexy and interesting as energy, but actually it's very exciting if you look at all the different parameters that it interlinks with. And unlike energy, which predominantly think about in winter or maybe sometimes in summer overheating, acoustics is 24/7. And so much depends certainly in our buildings, in our schools, our classrooms, our homes, everything that we do in the sound and the acoustic quality around us, and also that sort of protection from the transmission of noise from other areas. So what I'd like to do is run through a kind of 2 or 3 key features of some of the aspects around about acoustics, some of the things that are coming down the pipeline. And when I mean coming down the pipeline, it's going to be a very interesting time. For some reason, I've just seemed to have jumped my entire screens. So let me just see if I can just move this on. There we go. I hope you can still see that slide there, if that's okay. So just give you a brief overview about the Centre for Future Infrastructure, where we're based. I'm based at the Edinburgh Futures Institute and also the School of Engineering at the University of Edinburgh. I'm going to touch on global growth and construction, why it's important with what's coming. Some of the key properties of acoustics, elements of building performance, what's next for the sector, and also a new technical standard. This is guidance only. It's not an ISO in its full shape and form, but you should be aware of it for what's likely to come. So I'm director of the Centre for Future Infrastructure, which is based at the Edinburgh Futures Institute at the University of Edinburgh, and I'm also chair of future construction in the School of Engineering. The CFI really is looking at a whole range of aspects in terms of sustainable infrastructures, digital and data-rich infrastructures also, and the incorporation of sensors and other aspects, or digital design, and how we incorporate digital design into future smart construction, smart systems, but also looking at end of life. And then new and retrofit infrastructure from large modular, large-scale infrastructure that we might build in the future. But the aspect today is probably of most instances of what we're doing around circular economy, low-carbon construction systems, and the relationship and the fantastic role that timber has to play going forward. My background is my PhD was in acoustics and noise and vibration in timber frame buildings. And then applied it into many other areas of the industry sectors, not just construction, but defence, vehicles, aircraft, all sorts of other things. And for the last 10 years prior to joining University of Edinburgh 18 months ago, I was director of the Institute for Sustainable Construction at Edinburgh Napier. But what we do is very much a holistic approach. And in that regard, I'd just like to talk just about the future. And the next 80 years is interesting time as the population will grow significantly. We're talking about 3.5 billion increase, and that will probably need to build about 1.2 billion new homes. With people living longer, divorce rates, separation, single households for longer periods of time when young and when we're older, we will require also an extension to that 1.2 billion of another 800 million new homes to meet the existing needs over the coming 80 years. So this isn't in 80 years' time, it's over the coming 80 years. And so collectively, we will require to build about 2 billion new homes. And that's going to require a huge amount of resource and infrastructure and materials. And there isn't going to be enough resource and materials to cater for that global build if we currently build as we built over the last 20, 30, 40 years. And therefore, resources of what we build will draw on the circular economy. They'll particularly draw on materials such as timber to be used far more widely in acoustics, for example, in the design of classrooms, offices, buildings, and also more housing. And as a result, because it's of such a renewable resource, it probably stands the test of time in the sense of how it will be increasingly being used over the next period of decades to come. And so in that regard, I'd just like to give you a sort of inkling of what does it mean to build 2 billion homes. Well, let's take the 29 countries of Europe, 570 million population, and the 320 million homes which are there. To rebuild or to build 2 billion homes in the next 80 years, and considering, of course, that acoustics interlinks with over 70% of the technical specification of a building, it's incredibly important we get it right. But 2 billion homes in 80 years is the equivalent of building Europe 6.25 times, with all the infrastructure and everything that comes with it. So it's incredibly imperative that we build in the right shape and manner. I'm probably speaking to a converted audience already, but timber will be a key parameter and product and resource going forward. And of course, as we move into what is effectively now becoming a fifth industrial revolution of net zero technologies and systems, there's a great opportunity for timber engineering to excel even further. And timber is a wonderful resource when we look at what we do in terms of acoustics. From the very point that the trees are felled, we will look at its structural stiffness and grading. And acoustics is used at the very outset. Many of you will be aware, some of you not, but actually acoustics is used to determine the strength grading in so many of the timber pieces that we now utilize today, in so many of the logs, and then how it's then cut and sliced up. And that acoustic signal allows us to determine the stiffness and Young's modulus of the timber, and then accordingly grade it. And big hats off to our former colleagues at Edinburgh Napier I worked with, Dr. Dan Ridley-Ellis in the Centre of Wood Science and Technologies, who led so much of this work, not only for the UK, but also for European timber sector and forestry sector in the grading of timber. And having done all of that, and then we're starting doing the specifications of those separating floors, for example, for houses, and getting that right, it's then a case of then moving it into off-site construction, making sure those joints and systems are done well. We may then test it, or we may register it through robust details, which I'll talk about later. Or you may use, for example, more recently, cross-laminated timber, but ultimately we want the building performance in all its shape and forms to deliver what we need. It's great to see timber being used so widespread in so many areas and in so many countries, particularly in large-scale buildings such as this, the one in Sweden, the Sara Cultural Centre, but also Oregon State University, the College of Forestry. Tremendous, examples of how we can use timber on very large scales. Timber acoustic properties, of course, it's non-isotropic, it's orthotropic, and that makes it, from an academic point of view, very exciting and very interesting. And with the wave speed along the longitudinal and fiber direction sometimes being 4 times faster than the radial across the grain, this creates advantages, but also disadvantages in terms of acoustics and other material properties. And it's important that we understand these features in how we design for buildings, how we design the timber that we use, but also in the modeling and the predictions going forward. The acoustic factors that we commonly use and refer to are stiffness, resilience, mass, absorption, and isolation. And it's incredibly important that we get this right. The great thing is, over time, certainly the last 20, 30 years, the role of timber has played a significant greater role in terms of how we're using it for stiffness and resilience and mass. More recently, more with absorption through wood and natural fiber bats, but also with wood panels to improve and tune the reverberation within, whether it's concert halls or other buildings. And isolation by the design of the structure and limiting the connection nodes. And there's more about this in the document, New Housing and Sound Insulation, I wrote previously with some colleagues, and there's a link to that entire booklet, entire 300 pages if you wish to read it when you can. As some of you may know, when we developed robust details many years ago, and I'm still involved with them, I'm on the board, and I also am one of the acoustic advisors. It was a great involvement right across the industry, involving house builders and product sectors. And we had 5 industry working groups, 119 committee members, and one of the working groups was for timber construction and timber homes. And I was so grateful to a whole range of companies right across the timber sector and the timber industry sector as a whole, in the federations, because they were fantastic in sharing their data, providing sites across the project, including masonry and steel. We had 72 sites and 1,400 homes that were built in 6 months to the new technical specifications, and we were all tested. But what it led to was a standardized approach towards joist depth and how we would specify. Floating floor treatments, FFTs, were then characterized, whether they be batten systems, floating floors, or other things. We optimized the performance and workmanship improvements, high levels of sound insulation, unimaginable probably 10 years previously, and it really was a transformational shift by the sector. Importantly, it put a few myths to bed, in that we were able to demonstrate how good sound insulation was in timber buildings, but other sectors had obviously knocked against it. It demonstrated the high levels that could be achieved, and it provided a great innovation route and UK to the sector. And this led to a whole series of details, which many architects now utilize and register for their sites. Importantly, we now, I think, have 65 robust details, and about 1.4 million homes have been built. And we have the world's most in-depth database on sound insulation of all constructions. We do inspections and sample testing, and that's been a great feedback loop, and that's coming back to what Diana talked about, what she was saying with WoodKnowledge Wales and what they've done in terms of that feedback loop and tracking and what's going on. And this has been a huge resource for us, but also for governments and industry sector as we've looked at the performance of acoustics. And one thing I wanted to touch on today was cross-laminated timber and mass timber systems. They don't always have good acoustic qualities. And I know we're commonly, as a sector, both in timber and other sectors, we like to lobby and promote the great things, Well, sometimes the acoustics of such systems of CLT and mass timber are often overstated. Yes, they provide structure and they also provide great stiffness, but some key aspects to consider about CLT and mass timber is they do have low density. They have a coupling transmission, which is very high between similar material properties. The material resonant frequency of those components are in the primary mid-frequency range during sound testing on your frequency graphs. And they must, and to sort of overcome these aspects and improve things, you must incorporate isolation and shielding very often of CLT and mass timber systems. If we do that right, we will achieve the great performance that they can deliver, provided we shield and isolate. And we must be conscious of flanking transmission, which can often be higher for such structures than for other areas. And very briefly, one of the very first CLT sites that was built in the UK, we were involved with that at an early stage, and we had advised the architects to be careful of these synergies. Unfortunately, the product supplier, which came from Europe for the CLT, decided that that wasn't important, and because it was okay in Austria or somewhere else, then it would be fine. Unfortunately, people need to realise that sound insulation requirements, particularly in Scotland and parts of England, when you look at where the critical frequencies are, where the resonant frequencies are higher in some respects than some of our European neighbours in terms of performance requirements. And also they have a different emphasis in some of the frequencies, such as England and Wales at low frequencies. But also in the UK, we test, particularly in Scotland, England, Wales, we do pre-completion testing. It is mandatory. In fact, we are the only country in Europe that does mandatory pre-completion testing at the rate that we do. Other countries do sample testing for their clients, but in fact here it's built into the building regulations. So there's a clear difference here, and people need to be aware of that. And I'm all for one for promoting timber, but often we see companies promote CLT and what its great acoustics properties are, and that's not quite the case. It's great in acoustics when we shield and isolate. So what's next? Well, we do need a standardized approach for CLT design and construct for apartments. It would be great that the whole industry was moving together as opposed to the different depths and thicknesses which are out there, and we have standardized details. That would really help promote and develop the growth of CLT and mass timber if that could be standardized better, particularly for acoustic specifications. It's good to see the growth in wood and natural fiber bats, and we definitely need more on-site sound insulation data so we can incorporate these types of specifications and wonderful natural materials, into our existing constructions that are out there and people utilize, but also assist acoustic consultants for some of the non-standard constructions where they do want to incorporate wood fiber or natural material insulations. Certainly a greater awareness of the absorption characteristics would also be good, and that would help acousticians specify wood and natural fiber insulations for a range of diverse building applications as well. One thing I often think about as we drive forward the thermal insulation regulatory standards, and we're kind of almost optimizing now in these coming years the maximum we can do in new build fabric. As we put more of that insulation in, the great thing is, if we're using a wood fiber insulation, it's really very positive in terms of its increased carbon sequestration. Unlike other materials, which are non-natural fiber insulations, as you increase the thickness or density of them, so their CO2 emissions increase. Sometimes we need to remind the sector of some of these other benefits as we transform and move into higher performing buildings. I just wanted to finish off, if I may, for 2 or 3 minutes. This is a new acoustic classification of dwellings. It's a technical standard. It's a guidance. It's not a full ISO. And this, what it does is provide a new kind of classification system, A to F, that looks at the acoustics and sound insulation performance of attached dwellings, such as terraced housing, semi-detached, or also flats. It also has, which I've not included here, information on noise from services to achieve a particular class or level. Now, whilst it is a guidance, and some countries may decide to ignore it because we already have other kind of classifications. For example, in Scotland, we have Section 7, Sustainability, which has a bronze, silver, gold. So we already have graded or classification systems for performance. But some countries may decide, or some clients may decide to use this technical standard, this ISO guidance, as a way of classifying their system. And there's a link there to a paper I wrote with Philip Dunbavin, a UK leading consultant there in noise and vibration. We wrote this to kind of raise awareness last year of what was coming in case clients started to ask for it. And one thing I draw your attention to is to get Class A or Class B for impact sound insulation further down there, that is pretty tough. And for some timber structures, it's going to be a struggle, and it will require some alternative approaches. So it's just a heads up, if clients are starting to say to you, I'd like Class A or Class B in sound insulation terms under the acoustic classification of dwellings, make sure that you're engaging with an acoustic consultant so you can deliver those levels of class and performance. Just finally, a huge thanks again to the Timber Federation, to TAB, to Robert and NMITE, and I wish all the students the very best in their forthcoming University Challenge. Thanks very much.
Thank you, Sean. That was, yeah, really impactful, and so necessary, especially obviously in dwellings, but yes, in the commercial building that our participants will be designing, where you've got multiple occupancy at different times, and classrooms and kitchens and quiet spaces. Yeah, it'd be really interesting to see how they develop. And can I hand over to our final speaker, Gwilym Still from Max Fordham.
Thanks, Tab. Hi, everybody. Right, I'll just get my screen up and then we'll crack on. So, is that coming through okay?
Perfect.
Great. So, hi, everybody. I'm Gwilym from Max Fordham. We do MEP consultancy, acoustics, sustainability, passive house, and a miscellaneous mix of other bits and pieces. I work on both passive house projects and as an MEP designer. I'm going to be chatting today mainly around the MEP side of things, but with a passive house slant, particularly for this project that you were looking at, which looks really interesting. So the running order for today then is to have a brief chat before we get into the technical side about things like form, massing and zoning, then to talk about ventilation, about how we might deliver heat to the building, talk a bit more about domestic hot water, and then a brief summary with some kind of suggested principles for you to follow. So my expected outcomes or hopes from this is that you'll go away with probably more questions than you started with, which is always good, but hopefully with some ideas and resources to have a look at as you crack on with the design. So form, massing and zoning, before we start talking about fans and boxes and where to put them and so on, hopefully you'll have seen this sort of diagram before. So it's a passive house classic with Hat Tip to Warm, who developed it for the UK. So you've got different massings of buildings ranging from the really thermally efficient at bottom left with a low form factor, which is a ratio of the heat loss area to the floor area, and ranging through to the really kind of thermally inefficient, like the cruciform bungalows up at the top right. And the figures in red in brackets are the typical insulation thicknesses that you'll need to achieve for kind of passive house levels of very low heating demand for a UK climate. So you can see there the impact that you can have just as a design stage with the architectural massing of a building. That's nice and kind of fairly simple from an individual house and things like that. It starts to get a bit more complicated for the buildings and the brief that you guys have here. And one of the key reasons to think about there really is that I'd expect you'll have some form of internal zoning where you've got at least kind of 3 different categories of space within the building. So there'll be some gym or exercise space, there'll be some kitchen space, whether it's commercial end or this charming domestic one, which is a lot tidier than mine at home, and also the pristine office space on the right hand side, where as well as a nice clean wall, they've got charming uniformity of pencil and absolutely no used pencils. I don't know why that's there. So that's important because obviously the spaces have different characters and different usage, but also to think about things like the internal conditions you might want to achieve within them. One example of those obviously is temperature. And the graph here is just showing for a couple of different spaces. So this is taken from CIBSE Guide A, what sort of temperatures you might want to achieve inside those spaces for people to be comfortable. The blue is a kind of typical wintertime range, and then the salmon pinky color stretching off the top is how high you might let it go during the summertime case. So you can see in here there's a fair spread between people wanting to be nice and warm in a changing room, which is understandable, through to wanting somewhere fairly cool for a sports hall because you're running around playing sports and you want to have a way of getting rid of heat. And then with corridors and offices and kitchens sitting somewhere in between, again with kitchens towards the lower end. So the main point to draw from these, I think, is that yes, aiming for a really compact, efficient form overall for the building is a brilliant idea, but don't do that at the expense of having lots of really inefficient internal zoning where you're going to have lots of unwanted heat transfer from a warm space into a cool space and vice versa. And also to think about that zoning when you're drawing initial concept diagrams and following things through. So on the ventilation side of things, so ventilation generally there, we're trying to provide fresh air and we're trying to remove or dilute pollutants. A common pattern for passive house buildings will then be to provide mechanical ventilation with heat recovery. And the diagram here is from a kind of generic cross-section of a passive house building showing some key features you would expect. So the MVHR unit put near to the thermal line of the building, because we're going to have a cold duct on the incoming air, and also if the heat recovery is working properly, we've got a cold duct on the exhaust air. So we don't want to pre-warm the incoming air because we'll reduce the efficiency of the heat recovery unit, and we don't want to leach heat out of the building with the exhaust air. And then a common pattern, once we've got that unit nice and close to the thermal line and we've got a really efficient unit, is to use a cascade approach. So you can see towards the bottom here, we're trying to supply fresh air into occupied spaces. So that might be an office space as an example, transfer it through circulation spaces, so corridors, etc., to make sure that they're still ventilated. We're still taking away VOCs and pollutants from people cleaning and that kind of thing. And then extracting from places like toilets and others where there's particularly noxious pollutants produced. One of the advantages of this approach is that it helps to limit the overall ventilation flow rates of the building, and that can help to reduce both the plant size and the capital cost of it, but also the operational energy use as well. So this figure and picture of an absolute M&E installation nightmare is from a really interesting series of webinars run by a Canadian called Monty Paulson, called A Pattern Language for Passive Housing for Affordable Housing. And as well as showing what can go horrifically wrong, it was just a really interesting idea he had in this set of talks about saying, when you're designing a building, have a crack at just thinking about the mechanical design and sort of lay that out first and organize the building around it. Now, obviously I've got a natural bias towards that sentiment as an MEP consultant, but I thought it was a really interesting exercise of saying, when you start with buildings and concept massings and so on, that's fine to have a go and say, my concept is inspired by nature, so I've drawn the building like a leaf, that's fine, but also have a go and say, well, my key strategy is to have a really efficient ventilation and low energy mechanical system. So what would a building look like if it started with that as the guiding principle? Not because that's necessarily your final design, but because it will give you at least a couple of different end approaches to start with and to synthesize as you work up the design. So here's some key points to think about for ventilation units really. So consider the design flow rate that you're going to want to have, but also figure out how far you can turn that down. So if you've got an office that's going to have 100 people in it, make sure that you haven't got a ventilation unit that's going to be running at a full flow rate for 60 people if you're going to have only 3 people in there most of the time, because you'll have them getting pretty dry with low internal humidity and you'll waste a lot of energy. Look at the heat recovery efficiency, and some manufacturers will give you how that varies with flow rates. I'll put a link in right at the end of the slides for this so you can have a look. Think about summer bypass as well. So that heat recovery is great in the winter time, particularly, especially for a space like an office. In the summertime, you can use the unit as a way of giving you some secure nighttime free cooling, and you can also use it as a way of purging heat from the building during the day. That only works if you've got a unit that does this summer bypass sensibly. Think about access for maintenance and replacement. So in your mind, you should be clear that the unit will break at some point. It's when, not if. And when it does, how are you going to get it fixed and replaced? Think about the noise side of it. So that's both from a kind of radiated noise and also duct-borne noise from the fans running down the ductwork. And think about how you're going to get it controlled to keep things nice and simple. One bit we've certainly seen on other timber-based projects is looking at the loading side of it. So if you have a timber frame, tying in how much structural load you're going to have from the plants, and figuring out if you need to have, I-joists at closer centres locally and things like that. And also having a think about how you're going to avoid vibration, noise, and transmission of that through the structure as well. So we'll now shift a little bit onto kitchens as a fairly special condition. One of the key bits with these to do a really efficient kitchen, I think, is before you get into a nice fan and everything running cleanly and so on, is to look at demand reduction. So reducing the amount of heat that's generated in the kitchen, because some of the primary purposes of ventilation in a kitchen are to get rid of pollutants, particularly incomplete products of combustion, grease and other particulates, but also to get rid of heat as a kind of pollutant. So the graph here is showing the kind of typical cooking efficiencies of gas appliances, standard electric, and then induction. There's some quite interesting articles online from Michelin-starred chefs who are moving to induction cooking, not because it's environmentally friendly, although it is, but because it just gives a more comfortable cooking environment. And so if you do that, the efficiency of the gas here means that basically you're dumping even more heat than you want to into the kitchen. That's not a great idea, and it means you need more ventilation to get rid of that heat. So induction to start with to help minimize the heat loss and efficient cooking appliances. Here's a couple of examples. So you can go from the kind of swanky domestic scale on the left-hand side to the even more esoteric induction wok burner on the right-hand side. So there's something for everyone in the range of induction. I should have bought shares in some sort of induction manufacturer, but I don't. There's a really interesting paper on low energy kitchen ventilation from Nick Grant and Alan Clark. There's a link to that in the references at the end. But the general principles were set the design up so there's no heating load to the kitchen. So that's both, there's no heating load to keep the whole room as an entirety comfortable, but also you don't have to put extra heat in to avoid cold drafts from the fresh air that you're bringing in wintertime. To do that, you need to consider at least two different scenarios. So they're shown in the diagrams on the right. The top one is the kind of prep scenario where you're not cooking, so there's not much heat being generated from the oven, etc. There is a bit of heat coming off the back of the fridges and things like that. The room is at 20 degrees and the extract is at about 20 degrees, but it's at about 30% flow rate or so. And then the second scenario here is when you're in a full-on cooking scenario. So there's much more heat being generated both from radiation and convection from the cooking appliances. The temperature of their being extracted then is up at kind of high 20s or so. You still want that supply air coming in to avoid being uncomfortably cold. And so that means in both of those instances, you need a bit of heat recovery. And to do that, you can use what's called a runaround coil, which gives you a kind of a fairly efficient way of recovering heat to the point where you don't need any space heating to supplement it. And if you combine that with some speed control on the fans and give the people in the kitchen a way of controlling it, then you can deliver that without needing any additional heat. So second scenario after our kind of offices and then kitchens is for gyms and thinking about thermal comfort for them. So one interesting part with this is the different ways that people lose heat and which ones of those dominate under different conditions. So the first example on the left-hand side is someone who's sedentary. For some reason in this diagram, they've got a seat and they get to wave their hands in the air, but there's no computer or keyboard or anything like that. So you can see there that heat loss is kind of dominated by radiation. And that's part of the reason that, you know, the passive house with triple glazing helps, because it avoids the radiant asymmetry and discomfort from that. And then there's a chunk from evaporation and a chunk from conduction and convection. When you shift up to really intense exercising, then the majority of that heat loss is from evaporation at 80%, with a little bit of radiation and about 15% convection and conduction. That's not because suddenly people have stopped losing heat through conduction. It's just because you can see on the graph here, as the exercise rate increases, the amount of evaporation ramps up. And so a way of trying to minimize the energy use of this sort of scenario is to really promote evaporation in whatever form you can. So as well as having, you know, well-designed and generous ventilation systems that will respond to demand, probably based on CO2 sensors within the space, you can use large volume, low pressure fans like these to promote air movements. This is an image from probably the best named mechanical supplier, Big Ass Fans in America. So it's very much the Ron seal of fans that does exactly what it says in the tin. And so things like that are quite nice as a way of then encouraging air movements, which you might want to avoid in an office, promoting drafts and the associated evaporative cooling that you get from those. So I think to tie those bits together, then you've got, you know, at least 3 different types of space within the building that you need to design for. They've got different internal conditions. They probably have different occupancy patterns. Those combined suggest looking at separate systems for each of them. It's definitely worth thinking about the strategy for those early on, and plant locations following those principles, but also figuring out how you're going to get the air from the plant into the space back out again. And it's also really key when you're doing, you know, kind of plant arrangements and things like that, to allow space for all the extra bits. So if you get a diagram of events or a size for a ventilation unit and plot that into a room and say, well, the room is bigger than that ventilation unit, I can guarantee the room is too small, and you need to allow all the space for attenuators and bends and dampers and miscellaneous bits and pieces that go with it. And then the last one is really just encouragement to sort of keep it simple. It's very easy to turn these kind of systems into something that's very complicated, or to get beguiled by technically advanced systems with lots of variable air volume dampers and things like that. I think a good guiding principle is start with the simplest possible thing and only make it more complicated if you're convinced that it's going to have a really big benefit. If it's kind of a 5 or 10% improvement, then it's probably not worth it, especially if you don't think you've got a client who's going to be capable of maintaining and tweaking something sophisticated or complex. So a few little bits on space heating then. I'm sure people are getting bored to death of heat pumps, but they're a really good low carbon way of delivering space heating. We've tended to find on passive house schemes recently that the additional capital cost of going to ground source isn't really justified for the low heating demands of a passive house scheme, and so we're tending to do more and more air source systems and fewer ground source. You can choose units that have a really low global warming refrigerant in them, which is worth doing. When you're doing that kind of system design, do think about zoning and times of use. Aim for something that's got a low temperature, so whether that is, you know, something like underfloor heating, or whether it's just reasonably sized radiators that will work with low flow temperatures, so, you know, 40 degrees or so in the winter time. When you're doing that, do also think about the kind of turn down for the shoulder seasons as well as the peak wintertime case. Because you're designing to a passive house scheme, that's good. It's quite useful in a way, because it lets you know that the peak wintertime heating demand for the space will be about 10 watts a square meter. So with your brief of about 800 square meters, that's about 8 kilowatts. That's kind of a domestic scale unit. So if you're coming up with a design that looks like it's from an industrial factory, then you've gone over the top and need to rein it back a bit. And do also, you know, factor into it this side of things as well, that there's going to be different comfort temperatures for different spaces. So think about how you're going to set the system up to achieve that. So again, a few considerations for those. So have a think about the peak loads, but also the shoulder seasons, and figure out how you're going to keep the system running efficiently when it's turned down to a low output. Find a place to put the heat pump. So think about noise, think about allowing air movement around it and keeping the pipework into the building nice and short. Come up with some internal plant space. There's a link in some of the stuff to the end that shows a kind of example schematic so you can have a go at figuring out some space. At least know that you'll need to have some things like weather compensation and controls in the system to make it work really efficiently. And also just have a think about how people will interact with the system. So you're giving people autonomy over the control of the heating within their spaces. Are you considering spaces as communal, so they just have a single set point and they just operate, or something else? And then a few little bits on domestic hot water, another glamorous topic. So some of the general principles of this then are try to put the water storage close to the heat source, because you're going to have some hot pipework between the heat source and the storage, and then try to minimize the distribution losses from there. So ideally having radial pipework and minimizing the recirculating pipes. This graph here is from an example study done from, I think it's the Energy Saving Trust. One of the bits is shown here, just going from kind of right to left, is the heating demand and the energy use going from a kind of UK basic system through to a really good one. The light blues in the middle are the hot water usage. So this is for 4 different scenarios with basically the same utility, the same amount of hot water being delivered. And the bits you can see in here is there's quite a lot of opportunities to reduce things like the storage losses from the cylinders, just through the sizing of the cylinder and the choice of it. The primary losses from circulating pipework getting from the heat source into the cylinder, and then the secondary losses from the circulation around the building. The other bit that's played out in this graph at the bottom is you can see a change in kind of actual space heating, which you'd expect to increase a bit if you have a system that isn't accidentally dumping heat into your house all the time. But the complement to think about with that is that that's fine for the wintertime case. You might be having a slightly higher heating demand, but in the summertime case, you also, with the basic approach, is increasing summer comfort or summer discomfort risk by, again, building a 24/7 radiator into your building. So common approach is to provide domestic hot water really efficiently, minimize the demand, so have low flow appliances. The kind of Star Trek style image at the top right is from one which claims to deliver a 4 litre a minute shower that people actually enjoy, so that's worth a look. Minimize demand through user behavior. So I quite like these ones, just a little egg timer that you can stick on the wall in the shower or something that lets people gauge how long they've been in for. Drive down the recirculation losses, so having a really lean pipework design. Minimizing dead leg losses, so radial arrangements using microbore pipework. And then once you've done that to get the demand down as low as you can, then generating the water really efficiently, so using a heat pump. With all that said, heat pumps aren't always the answer for really efficient domestic hot water delivery. So it's worth thinking about what the actual usage case scenario is, how much recircular loss you're going to have, and the summer comfort risk. There are some instances where points of use delivery on an instantaneous basis with direct electricity make more sense. That's certainly been the case on a few projects we've looked at where we've had kind of disparate toilets or things like that, where people don't use the water very often. And even in a global pandemic, I found it depressing how low the hand washing ratio is in a gents toilet. So yeah, caveat emptor with that. And this is also one of the things which you can use PHPP to test for and set up a couple of different scenarios and see which one makes sense. So in summary then, make sure you understand what you want to achieve in the different spaces through the building. Definitely draw the thermal zoning onto the systems really early. Try to minimize the demand as far as you can and then deliver it efficiently, and really keep it simple. Here's a whole load of miscellaneous references from Big Ass fans to AHU selection software. So have a flick through those. And if you've got any questions, then I'm happy to answer them in the Q&A. Thank you.
Thanks, Gwilym. Yeah, really appreciate it. See, I think all this stuff's sexy. Obviously I'm a bit strange, but yeah, if we don't understand the basics of as Diana said at the beginning, you know, you're delivering your sort of your hot water and your energy usage and the comfort of your home, and it's not working properly, then, oh yeah, sorry, it drives me nuts. There are a few questions, and then I'll open the floor. And great to see my colleague over there. I'll wave at the other side of the room. There's Robert over there. So first of all, questions from Stephanie, and this is to Sean. Wants to understand more about frequencies and why they're different in different countries. And this is to do with the proximity to airports or densely populated cities.
Actually, neither. It was predominantly because the sound insulation in attached housing, there were various historical records of noise complaints, so particularly for low frequencies and hi-fis, etc., back in the 90s, and that started a sort of chain reaction looking at low frequencies. And instead of extending in England and Wales the frequency range from 100 hertz to 50 hertz, instead of extending it downwards, it's quite difficult to measure. Our rooms we build in the UK are generally quite small volume, so it's difficult to measure low frequencies. So as a result, they brought in a weighting factor called CTR, which was for traffic noise, originally used for facades of buildings, but they then introduced that into separating walls and floors. So in England and Wales, they only go to 100 hertz, like Scotland and Northern Ireland. The same in Ireland, we go to 100 hertz up to white noise, kind of 3,150 hertz. But in England and Wales, they put an emphasis on low frequencies using CTR. Other countries, France, Sweden, particularly Sweden, they will go down to 50 hertz for their building regulations. And in some cases now we'll go down to 20 hertz. So quite considerable change, but driven predominantly by how people are living, etc. But we also adapt the facade sound insulation in different countries, but that's predominantly is for what is the external source, such as near roads or airfields.
Brilliant, thank you, Sean. And I've got a question for Gwilym from Ocean. What's the best way to managing the varying humidity throughout the building zones?
Yeah, good question. I think one way to think about it is that water is both, you know, low humidity is a problem for spaces, but also high humidity. You can treat water effectively as a pollutant, and so often that's dealt with by providing the right level of ventilation. So you don't want to, you know, over ventilate an office space in the winter time, because you'll be bringing in lots of cold, dry air and then warming it up and leading to low relative humidity and, you know, discomfort and likely increase of infection and things like that. And you don't want to have inadequate ventilation, because that leads to high relative humidity. So generally having ventilation systems which will either be sized to deliver the right flow rate or controlled to respond to internal conditions, whether that's based on RH sensors or something else that's going to be a good proxy indicator. So, you know, CO2 levels from respiration map moderately well to, you know, moisture emissions from people, or just giving people some control as well. So, you know, in a kitchen, letting the chefs have a speed controller for the fans is a good way of doing it.
Thank you, thanks Gwilym for that. And Diana, have you come across like on when you've been monitoring buildings about, you know, real high humidities in different areas and different rooms?
We haven't come across one of a particular, you know, like a problem with humidity, but to be honest, we only deal with small scale social housing. And the first stage of the Homegrown Homes project was predominantly new build. I expect now that we're going to be moving into the retrofit area, we're probably going to be coming across more problems with humidity. So I'm going to be reading a lot of your references. And
that's what I love about, you know, our speakers, everybody's learning from each other as we go along. I'm going to ask this question to all of you, because I think partly it's based around an aversion to passive house and still thinking that it's like living in a sealed plastic bag and you can't open windows and doors and things. So Zoe's asked about how about natural ventilation. So I'm not sure who wants to take it first, but I think I'd like all of you to comment on it, if that's okay. Yeah, Gwilym's go first.
Yeah, go on then. Yes, let's have some. I think so. It depends on the application. I think a lot of times on passive house schemes, they're in the UK climate, they're a hybrid scheme where you would provide good levels of ventilation by an MVHR system through the winter, so there's always good indoor air quality. And then in the summertime, natural ventilation would be part of a summer comfort strategy. Obviously, that applies a bit less to, say, a commercial kitchen, where you need to have really reliable, very high ventilation flow rates, and it applies more to, you know, an office space or a sports space where you might be able to create a lot of air movement, and do it in a way that people will still enjoy it and feel comfortable.
Brilliant, thank you.
I also wanted to comment in natural ventilation, because I'm a big fan of natural ventilation. But obviously, the more airtight we design of buildings, the more then we have to rely on occupants making sure that the place is naturally ventilated. And as we know, that doesn't always happen. A lot of people don't want, you know, they prefer to keep their houses warm by keeping the windows closed. And that's when we then introduce a lot of potential problems into the building by not ventilating these spaces properly when they are so airtight. So it's something that I believe we should be doing a lot more research in that area on what would be the best way to encourage natural ventilation in these airtight buildings, because at the moment the best solution is to provide mechanical ventilation. But I would like to see more work in that area, to be honest. And yeah, Gwilym has his hand up, so I'm sure he's going to have something really good to say about this.
I was just on a from a personal case study, given the pandemic, I bought one of those little portable CO2 monitors, and I can definitely testify that we've inadvertently prioritized thermal comfort over indoor air quality in our house, and have to rely on it kind of beeping to go and open a window, because otherwise the default is just to leave things closed. And so I think for a low energy building, like a really low energy building we're looking at now, a hybrid approach is good, but it's definitely use something that's really simple and reliable for the air quality side of it, and look at the nat vent side for the summer comfort side.
Thanks, Gwilym. And Sean?
Well, I'll kind of sit on the fence, if I may, if I'm allowed to. So I prefer natural ventilation. Part of the reason is we have tested buildings which have, you know, really high passive levels, good passive levels of performance, and then some years later it's not as airtight and everything else. And in fact, actually, we've put in this MVHR, we've done all this thing, the building's moved over time, the occupants change how they use things, and actually, what is the carbon footprint of all that, you know, embodied energy we've put into having an MVHR? That said, I've also seen where people have passive houses, they love them, they really enjoy it, they find their heating bills are really low, provided they know how to use it. We've also seen the extremes. We've seen people who have had passive houses, both very deprived areas where people have moved into a passive house, and very rich, wealthy people who've moved into, and both have done the same thing. They both said, my energy is so cheap, I'll just use more. So there is a compounding influence that goes on here. But I have to say, from an acoustic standpoint, so if I can step onto that chair very briefly, the more airtight we make the building, so the issue is our hearing becomes more sensitive. And the primary reason is that we don't have that natural dissipation of pressure that would happen within the building. So when people are moving around in flats and apartments, for example, we sense and feel the people upstairs because of that low frequency pressure change. And if there's not that release of pressure in the building as there used to be, we actually sense and feel exactly where those people are. It will sail through the building regulations and pass by a mile, but the people will tell you, oh, I know exactly where my neighbors are upstairs. So there are indirect knock-on effects that probably when it was first thought out and everything else. But I think in detached, terraced, attached housing and homes, yes. For apartments, I think the jury's out a wee bit on some of it. Thanks very much.
And I think that's the almost like the beauty and complexity of buildings and views and you know, everybody's experience, and it changes, doesn't it? You know, and a really good example can really change people's opinions, and a bad example can just cut something dead, and it is just because people didn't understand it and didn't get it right. Yeah, it's utterly shocking. So we've got, I think we'll just take this as a final question. So it's referring, referring, Sean, to what you said. You're preaching, you think you're preaching to the choir here about that everybody here in the audience sort of loves timber, or at least understands it, wants to use more of it. But what are the opportunities to spread the message about timber outside of this industry? And I think Stephanie said, like, outside of this parish. And I think you can probably all answer that, and Robert probably as well.
Yeah, I was going to kick off to say I think everyone should answer this. So I'll keep my answer brief. I would use the Robust Details project as the example of how we changed myths. We worked really closely with the industry. We got the data from all sectors. And when we started to publish the performance data, non-timber industry sectors were not happy because they had blasted myths about timber of how it didn't perform, and actually demonstrated it did. So part of it is the sector preaching to the non-converted, and I like that phrase of the parish. So those who aren't believers, we need to get beyond the parish and extend our reach of here are all the benefits. And at the same time, we need to work with, the block and concrete industry. There are hybrid constructions coming involving timber and block systems, really rapid block systems coming to the market soon. Really exciting stuff, and we need to build 375,000 homes per year for however many years, and we only did 275,000 in a good year. So we're going to need everybody to work together. But yes, let's get the reach beyond. And what we did was we went to building control, we went to building standards officers, we went to a whole range of people in industry and said, here are the performance levels. So we went outside the box, and that would be my strong recommendation.
Before I hand over to everybody else, which I'm sure what's name, how do we then get that more taught in schools, Sean? Because, architects, engineers, they're still learning very little about timber.
Yeah, and I think this is a case for RIBA, RIAS, and others, particularly in the architecture schools, to get their technology lessons right. And that includes CIAT, the Chartered Institute of Architectural Technologists, and also civil engineering, ICE, iStructE. There's a lot of great characteristics of timber and performance factors we need to get in front of people. We should not be using textbooks from 20 years ago or 10 years ago. Things have moved on.
Oh,
I'm not promoting Robert's book there, but it's a great book.
Nothing like a bit of nepotism from university professor colleagues. Diana, do you want to take it next?
Yeah, I wanted to share our experience. As I say, we're not at the moment focused on academia. We're working with local authorities and housing associations and promoting the use of timber with evidence-based arguments. And there's still a lot of reticence. I just want to share one comment when we went to one of the local authorities when they were planning on changing the windows of a particular project, and we asked them, well, have you thought about timber windows? Have there's some modern design timber windows that are really highly efficient. And the answer was like, yeah, we know a lot about timber windows. We're taking them all out because they're talking about the ones that were installed back in the 70s or 80s that were really badly performing buildings. So I think more than trying to convince people with all this evidence-based information that we have nowadays, is more about, as Sean mentioned, trying to break the myths that of people that have it. And there's not so much of a myth that they have bad experience with badly installed timber, and we need to let them know that we are in a different scenario now, that we know a lot more, that we are aware that a lot of mistakes with timber were made, especially in the UK 20, 30, 40 years ago, and those mistakes are we're having to correct them, but that doesn't mean we have to correct them by putting a lot of plastic windows out there, but just by looking at what are the actual timber windows that do work. And similar comments we get from, for example, retrofitting projects where they badly installed external wall insulation, for example, and then we're getting a lot of housing associations coming to us saying, no, we don't want external wall insulation, we'd rather put a PV on the rooftop, when we're trying to promote the story of fabric first approach. You first need to minimize your demand before you try to bolt on a lot of technology to provide renewable energy. But because there's so many badly installed items like insulation or timber windows, or there's a lot of examples out there that don't help our case. So we need to go and find the right arguments to actually convince these people that are in the work of fixing the problems that badly installed timber created in the past, and trying to tell them the solution is no go still concrete and plastic, is rethink timber again and do it right.
So also like an education and training program for the installers and the construction people, as well as the designers and engineers and specifiers. And Gwilym, do you want to?
I'll have a crack, yeah. I think making sure that there's information shared, it becomes easy for people to adopt, and making sure that it is clear and straightforward on the pros and cons. So, you know, like Sean was talking about, the flanking noise and bits of CLT and things like that, so that people don't walk into mistakes or problems which are easy to avoid. I think talking to engaging with some of the gatekeepers, so particularly, you know, like property insurers and things like that, where that can become a real barrier to the adoption of you know, timber-based projects. We see that crop up sometimes, and also sharing example projects, particularly completed ones, which are really, really nice buildings, because often clients won't want to be at the bleeding edge of a technology. They want to be towards the leading, but definitely nice, safe and comfortable edge of that technology. And so showing something where there's 16 precedent examples of clients who are absolutely delighted and enjoy their timber-based buildings is a nice way. And I think picks up on the point Diana was making about, you know, it's very easy to find scare stories about practically any technology out there if you've got a large enough sample set to pick from.
Brilliant, thanks, Gwilym. I'd never heard the bleeding edge before, so yeah. I mean, obviously, I'm not at that rate of cutting it. So, and I think this is teed up very nicely, Robert. If I'll share screens after you add about how do we get more timber understood.
Perfect. I think first and foremost, just to thank all the speakers for this evening. Fantastic. I think, the information that's getting out there to the learners, and there's those that are tuning in this evening, but obviously Tabitha's probably going to move on to recording all of this, and it goes on the YouTube channel, because Tabitha does this amazing job of pulling everything together, and then getting information out there. And I think that chimes with what's been said in many respects. As the mission that we're on at the moment is to try and democratise this content as much as possible, so we can make a shift in the level of understanding. So that as much as this is for the learners, etc., that participate in the challenge, there's the conversation that we're having this evening, and then there's the broader impact that this can create in terms of how we promote the content. So as much as sticking with Sean's acoustic team, perhaps this might be an echo chamber, but hopefully we'll amplify it outside the parish and into the wider community as such to make that difference. And I think just the other piece on that for me is with construction and the sort of traditional business model procurement approaches, which lines up with what we're doing tomorrow, Tabitha, right? And how we can change the emphasis of that, so we think about it more in terms of that value proposition, the value piece, whole life cycle impact, not just about cost, but indeed about environmental impact and the cost that that's having on our planet, and hence why timber and renewable natural capital is a better form for delivery of the built environment. So the more that we can get this technical content in it and use that and infuse that with the broad understanding of value, I think more we can make a difference. So with that, I'll hand it back to you. But thanks very much to the speakers this evening.
Yeah, no, I echo you. I mean, I'm always amazed and how well our speakers all like hang together as well, when they often don't, know who's coming before them or after them, and it just neatly sort of somehow dovetails. It's absolutely amazing. No, thank you all. I want to, if we'll hold on until I've just got a few slides to share, if I can get it all right and not make a right mess of it now. So if you'd like to join us on Thursday, you can learn all about homegrown timber, where you have the pleasure of Robert and Sam and Luke and Wojciech and see, I haven't got my notes in front of me, Matt. speaking all about what they've been doing in transforming timber. And they believe in it. They don't only believe about learning about it and doing it and disseminating the information, they're actually our major sponsors too. So you'll come and learn all about homegrown timber, insulation, CLT, and so much more. And I'm sure Robert can fill you in more on that. Now, can I move screens? That's my my next thing. Oh, there you go. But again, we have to say, not only thank you to our sponsors, our speakers who come and give their time freely and disseminate this knowledge, which is so essential to taking everything forward. But we couldn't put on this this challenge without sponsors. And there are cash prizes for participants. And we're also going to take them down to Hereford to see the new CAT building, which is CAT with a double T, the Centre for Advanced Timber Technology. And so apart from Transforming Timbers, thank you to Wood for Good, PFC, Timber Decking and Cladding Association, Passivhaus 15, Accoya, Stora Enso and Rotherblast, and our software sponsors. So we will be counting carbon, and it will be using the AECB carbon calculator. It will be designed to Passivhaus, so design pH and PHPP will be provided to all the participants, and those two dovetail in together, and then they all lock together with the Trimble software. So not only are you going to get the SketchUp, you're going to get the whole Trimble platform for a whole year. And yes, with that, I'd just like to say good night. Hope to see you again on when are we coming back? On Thursday.
Fantastic. Thank you for having us, Dab.